Hello everyone and welcome back. This is screencast number 2 for Chapter 20, Conventional Energy Alternatives. And as I said at the end of the last screencast that we were going to focus on nuclear energy. Nuclear energy is a little bit complicated, but before we do that, let's just take a look at this table, of the top producers of nuclear power. So we can see that United States is the leading producer. We've got about 104 reactors, and as we already discussed, about 19% of our energy for electricity comes from nuclear power. We have so much that we could really generate a lot more. We see that France has about 58 reactors, and with those 58 reactors, and remember it's a little bit of a smaller country, almost 75% of their energy comes from that. Japan takes the next step, but only gets 2%. Most of their energy they rely on is from coal. And then we can go down. Germany is considered one of the leading ones, and believe it or not, Sweden, as we've already talked about and as you read about, they only have 10 reactors, and 38% of their energy comes from that, and we already know that they use other conventional alternative methods in addition to this. So let's take a look at nuclear energy and learn a little bit about fission. So nuclear energy, here's the definition of it, is the energy that holds together protons and neutrons within the nucleus of an atom. And what we do is we harness this energy by converting it to thermal energy inside a structure called a nuclear reactor. Nuclear reactors are facilities that contain within nuclear power plants, and this is where thermal energy is then used to generate electricity. The reaction that drives the release of nuclear energy inside nuclear reactors is called nuclear fission. And simply put, it's the splitting apart of the atomic nuclei. We use this splitting apart of the nuclei for the energy of nuclear power plants. Sorry for that pause. I was just trying to think there's something missing in between those two bullet points. Let me go back a little bit. So when we split the atomic nuclei apart, we're using the nuclei of very large and heavy atoms. Atoms like uranium and plutonium. And what we do is we bombard those atoms with neutrons. And based on what you know about neutrons, hopefully you remember this from chemistry because you had an excellent teacher, neutrons move very quickly and sometimes too quickly to split the nuclei when they collide with them. But by slowing the neutrons down, they can actually break apart the nuclei. And each split nucleus emits energy in the form of heat, light, and radiation. It also releases multiple neutrons, so we can then use those neutrons in turn to bombard other nearby uraniums. With uranium, since we're using that as an example, 2 to 3 uranium-235s would be used and bombarded, and the atoms resulting in the self-sustaining chain reaction is going to produce energy. Now this has to be controlled. That's one of the important factors with this. Well, here, let's take a look at this before we go further. So this illustration actually shows nuclear fission, and it shows the nucleus of an atom. So here's that uranium-235 that we were talking about, and it's going to be bombarded with a neutron that has been slowed down, and it's going to break the nucleus of this uranium up, and that's going to release energy, as we said, in the form of heat, in the form of light, and in in the form of the electrons and the neutrons that are going to be released. So here's a fission fragment because it breaks apart. Here's another fission fragment because it breaks apart. So the collision splits the uranium atom into smaller atoms and releases 2 or 3 neutrons along with the energy in the form of heat, light, and radiation. The neutrons can then continue to split uranium atoms and set into motion a runaway chain. And engineers at nuclear power plants then absorb the excess neutrons and control rods to regulate the rate of the reaction. So this is how we get that energy. Okay, so if this is not controlled, the chain reaction becomes a runaway process of positive feedback. The process that boy, I can't even talk this morning. The process that creates the explosive power of a nuclear bomb. So this is where society has concern about nuclear power, of course. Inside a nuclear power plant, fission is controlled so that on average only one of the 2 or 3 neutrons emitted with each fission event goes on to induce another fission event. So we have a way of controlling those neutrons. In this way, the chain reaction maintains a constant output of energy at a controlled rate where it could not be used in the form of an explosive power or nuclear bomb. For fission to begin in the nuclear reactor, the neutrons bombarding the uranium are actually slowed down, and it's slowed down with something we refer to as a moderator, which is usually water or graphite. Graphite is what you find in your pencils that you use to write with. And as fission proceeds, it becomes necessary to soak up the excess neutrons that are produced when the uranium nuclei divide, so that on average only a single neutron from each nucleus goes on to split another nucleus. So we also have inside of the power plant something called control rods, and these are made of a metallic alloy that absorbs the neutrons. Then engineers will move these control rods into and out of the water so that they can maintain the fission reaction at the rate that they desire. All this takes place within the reactor core, and it's the first step in the electricity generating process of the nuclear plant. The reactor core is actually housed within a reactor vessel, and then the vessel and the steam generator and any associated plumbing are often protected with a containment building. This containment building has walls that are a meter thick of concrete and steel, and they are constructed this way to prevent leaks of radioactivity due to any accidents or natural catastrophes like earthquakes. Not all nations require this kind of containment building, and that's why it's important for governments to regulate and be actively involved for the public safety. Alrighty then, so this is what a nuclear reactor would actually look like. So this is the inside that we were talking about. So we are going to see that in this first area, these are the control rods that are going to be able to be moved up and down, in and out of the water. And the control rods will absorb any excess neutrons to regulate the chain reaction. And they're going to be surrounded with water. As we can see, this is where the water is going to be in this, and that water is going to circulate through the primary loop that we're seeing here. Okay, so that water is going to be heated up. As the water warms, it's then going to go into the secondary loop, and as it warms, we know it expands, so this is going to go up on its own power, and it's going to be converted into steam, and that steam is going to turn the turbine. and that turbine is going to work the generator that is going to produce electricity. So the steam then is going to be cooled. Here's our cooling process. It's going to come in and it's going to go to the cooling tower and come back. Some of the steam is given off to release the pressure, because we know that steam can create a lot of pressure, but the majority of it's going to come back after it's been cooled and re-enter that secondary loop so that it can be heated again in the primary loop. So fission is going to occur in this reactor core where the fuel rods are submerged in the water, and the water slows the neutrons in order to initiate the chain reaction in the uranium-235 in the fuel rods, while control rods will absorb the excess neutrons to regulate the reaction. So that is how a nuclear power plant is going to work. And this containment building, as we said, these walls are over a meter thick of cement and metal, probably steel supports inside of there. So we mentioned the use of uranium, and in this section I want to explain why uranium. And uranium is radioactive. We call it a radioactive isotope or a radioisotope because it emits subatomic particles and high energy radiation as it decays into lighter radioisotopes until they ultimately become stable isotopes. The isotope uranium-235 decays into a series of daughter isotopes, meaning different kinds of isotopes, and it eventually will form lead-207. Each radioisotope decays at a rate determined by the isotope's half-life. And a half-life can be a little bit hard to understand, but if you think of it in the way of the time it takes for half of the atoms to decay, that is the half-life. So for uranium-235, it has a half-life about 700 million years. So it takes 700 million years for half of those atoms to decay. Long time. So that's one of the positive things about using uranium. But to obtain uranium from various minerals in naturally occurring ore, and ore is rock that contains minerals of economic value, uranium-containing minerals are uncommon. And what happens is this means that uranium is a finite supply, meaning we have a limited amount of uranium. We don't have an endless supply of uranium. So nuclear power, because of this, is considered a non-renewable energy source. 99% of the uranium in nature occurs as an isotope in uranium-238, but uranium-238 does not emit enough neutrons to maintain a chain reaction when fissioned. So we use uranium-235, which just means it has 3 fewer neutrons, and this makes up about less than 1% of the total amount of uranium. Uranium-235 is used for the commercial nuclear power, and therefore we must process the ore we mine to enrich the concentration of 235 uranium to at least 3%. The enriched uranium is formed into pellets of uranium dioxide, and then these are incorporated into the metallic tubes called fuel rods that are used in the nuclear reactors. After several years in a reactor, so they can last for several years, enough uranium has decayed so that the fuel no longer generates an adequate energy and it must be replaced with new fuel. There are some countries that spent fuel is reprocessed to recover the remaining usable energy, but this has proven to be very costly, and uranium prices are relatively low, so they don't want to increase the price of the uranium. So most spent fuel is just disposed of as radioactive waste. Okay, so this is looking inside.